Okay, now I'd like to continue talking about vectors and discuss coordinate systems and how to add vectors algebraically. Okay, so we're used to the idea of coordinate systems, and you've been studying them, I hope, ever since middle school or high school. So what you do with a coordinate system is you choose your fixed point of origin, which is in the center of your coordinate system. You define that as your 0 point, and then you choose directions for your axes, and you appropriately scale and label those axes. Okay, and then you define the coordinates of a point relative to that origin. So, for example, you might be used to the Cartesian coordinate system or the rectangular coordinate system, which has x and y axes that intersect at an origin. And then you give the coordinates of a point. For example, if something had an x coordinate of 5 and a y coordinate of 3, then you would give those in 5, 3. And then you might have units of meters on your x and y axis, for example. Okay, so that's the Cartesian coordinate system and Cartesian coordinates. But there's other kinds of coordinate systems, and I hope you might be familiar with them. One of them is the polar coordinate system, okay? So instead of x, y data points in the polar coordinate system, what you do is you give the distance from your origin to your point of reference, and then the angle, okay, from, say, an axis like the x-axis that you have to swing up to in order to meet the line that connects your origin to your point, okay? So instead of x comma y, you give r comma theta, okay, where r is the distance and theta is your angle. It's easy enough to switch between polar and Cartesian coordinates. All you have to do is use a little bit of trigonometry. So in your Cartesian coordinate system, you chose the coordinate system usually such that there was a right angle between your x and your y axes. So that means that for any point, you're forming a right triangle, where the legs of the right triangle are your x and y axes, and r is your hypotenuse of the triangle, okay, that connects the origin to the point in question. And then if your angle is defined here as swinging counterclockwise from that plus x axis, then you can write your x and y coordinates in Cartesian coordinates via the equation x is equal to r times the cosine of theta. And then the y coordinate would be r times the sine of theta, okay? And this comes from our definition of the sine, cosine, and tangent of an angle. So remember that for the sine of the angle, it's the opposite over the hypotenuse. So here, theta, the y leg of the triangle, is opposite to my angle theta. So that's the opposite over my hypotenuse. The cosine of theta is the adjacent side to the angle divided by the hypotenuse. And then the tangent of the angle is the opposite over the adjacent. Okay, so you might remember that. And this equation will always work for switching between your x and your y and your polar coordinates. It'll work always as long as you define your angle as swinging counterclockwise from that plus x axis. Now you can also figure out, going from Cartesian to polar coordinates, you can figure out what the polar coordinates are by using the definition of the tangent, where you put your y and your y over your x leg of the triangle, and that gives you the tangent of the theta. So you can take the inverse tangent of y over x to get your angle theta. And you can figure out what the length of the hypotenuse is by the Pythagorean theorem, right? So here, x squared plus y squared would equal r squared. And so you can find out your hypotenuse from the square root of x squared plus y squared, okay? Yet again, these equations will always work, but you have to define your angle theta as swinging counterclockwise from that plus x axis. All right, so here's an example problem for you. The Cartesian coordinates of a point in the plane here are minus 3.5, minus 2.5 meters, okay? And that's shown here in this quadrant, this lower left quadrant. So find the polar coordinates of this point, okay? So your length, r, from the origin to the point would be the square root of x squared plus y squared, which is the square root of negative 3.5 squared plus negative 2.5 squared. And when I do that math, I get 4.3 meters. And then from the equation for the tangent of theta, I get tangent of theta is equal to y over x. So I can find the tangent of theta is negative 2.5 over negative 3.5, which is 0.714. And then if I take the inverse tangent of 0.714, I get 36 degrees, okay? Now, I know that's not right because my angle swings counterclockwise from that plus x-axis, and I know that it's in that lower left quadrant. So what I have to do to get it in terms of the actual angle to swing from that plus x-axis is I have to add 180 to that number, okay? Because I know that I'm swinging from x to y, or from my plus x to my negative x-axis, which is 180 degrees, plus the 36 degrees, and that gives me 216 degrees, okay? So that'll tell me what I get for my angle. Okay, well, you're thinking to yourself, she's talking a lot about coordinate systems, and what does that have to do with vectors? Okay, so here we go. You've got to define the vector in terms of the direction and the length, okay? And so what you're going to do a lot of is break a vector into what is called its components, okay? So what's a component? A component is a projection of a vector along a specific axis, okay? So for example here I have my vector A, which points in that xy coordinate there, so it's going up and to the right, and it's got an x component, which is its projection along the x-axis, and it's got a y component, which is its projection along the y-axis, okay? These are its rectangular or its Cartesian components, okay? And this is the same, for example, as giving the xy coordinates for the point. Okay, so here's my x and y component vectors of A, and if I add my vector A sub x to my vector A sub y, I'll get my vector A, okay? But if I want the magnitudes of those vectors, AX and AY in italics here, those are scalars, and those are my components of A. Okay, so like I said, if I add my vector AX to my vector AY, I get my total vector length A. If I do my tip-to-tail vector addition, it looks like this. Alright, so I can find the x components of my vector as projections along the x and y axes using the equations that I found for my polar coordinates. Now instead of r, which is my polar coordinate, I'm going to use the magnitude or length of my total vector A, okay? And then the x coordinate, A sub x, or the x component, would be the length of the vector A times the cosine of the angle theta, which it swings upward from the plus x-axis in a counterclockwise way. So AX is equal to A cosine of theta. The same kind of idea for my y component of my vector. A sub y would equal to the length of my vector A times the sine of theta, where theta is my angle from that plus x-axis. This assumes, of course, these equations assume that my angle theta is measured counterclockwise with respect to my x-axis. If the angle is defined with respect to some other axis, say the y-axis or the negative x-axis, then you either have to do one of two things. You have to figure out what the angle from the plus x-axis is swinging counterclockwise, and that's pretty easy to do in terms of, you know, adding or subtracting 90, 180, 270 degrees, okay? Or you can not use these equations and just use trig, okay? So if you like trigonometry, go for it. Otherwise, you can figure out the angle as it swings counterclockwise from the plus x-axis. Okay, and then if you want the length of your vector A and you know its components, you can figure that out too. The length of your vector A is the square root of the sum of the squares of the x and y components of your vector. And then the angle will be the inverse tangent of the y component of your vector over the x component of your vector. All right, so the components can either be positive or negative, and they'll have the same units as the original vector, just like the Cartesian coordinates for a point would. So in quadrant 1 here, your x and your y components are both positive. In quadrant 2, you'll have negative x components and positive y components. In quadrant 3, both your x and y components will be negative, and in quadrant 4, the x components will be positive and the y components will be negative. Okay? The angles will vary depending on the quadrant. For quadrant 1, the angle will be between 0 and 90 degrees. For quadrant 2, it'll be between 90 and 180 degrees. For quadrant 3, it'll be between 180 and 270 degrees. And then for quadrant 4, it'll be between 270 and 360 degrees. Now, you're definitely going to want to do the algebraic or component method of adding vectors if you want accuracy. Graphical addition is great for giving you kind of a general idea about the length and the angle, but if you want it to be perfectly right, then you need to go ahead and do the math. So if you want to add two vectors to get a resultant vector, so I'm going to call my resultant vector here R, and the vectors that I'm adding A and B, okay? Then what you do is, to find your R vector, you're going to add the x components together, okay? So it's going to be AX plus BX, and that'll give you your new RX component. And you're going to add AY plus BY, and that'll give you your new Y component, okay? And then the length of your vector, your resultant vector, will be the square root of the sum of the squares of Rx squared plus Ry squared, and then the angle will be the inverse tangent of Ry over Rx. So one of the important things that you want to do and always understand is that when you're adding vector components, you only add the x components together, and then you only add the y components together. You never add x to y. You don't want to do that. So Rx is equal to Ax plus Bx, and Ry is equal to Ay plus By. Okay? So note the relationships here. If I do the graphical addition, you can even see how that works. Here's my vector A added to my vector B, giving me my resultant vector. If I look at what the components are for our vectors A and B, you can see that the x component of my resultant vector is only the x components added together, and the y component is only the y components added together. Okay, before we get into the problems for this chapter that involve graphical and algebraic addition of vectors, I want to say one quick word about how they work the notation for north, south, east, and west. Okay? The general way to set up a coordinate system for these kinds of problems is you set it up so that north is your plus y-axis, south is your negative y, east is your plus x-axis, and west is your negative x-axis. Okay? If you say something is southeast, then what you mean by that is it's halfway between the south and the east axes. And that would mean that it's 45 degrees from either axis, since there's 90 degrees between south and east. It's halfway. Sometimes problems are going to say things like 53 degrees north of east, okay? And this is indicated in blue here. So what that means is that you start at east because it's north of east. So you start at east and then you swing towards the north by 53 degrees. Okay? So in this case it's counterclockwise by the plus x-axis. But it doesn't have to be that way. They could specify, for example, 45 degrees south of east. Okay? And that would mean that you start at east and you swing south by 45 degrees. All right? So that's the way they phrase things in these problems. And it can be a little confusing, so don't let yourself be fooled. Okay, so without further ado, let's go into an example problem of how to do this graphical and algebraic vector addition. So here we go. We have a hiker, and she begins by first walking 25 kilometers southeast from her car. And then she stops and sets up her tent for the night. And then on the second day, she walks 40 kilometers in a direction 60 degrees north of east, at which point she discovers a tower. Okay? So determine the components of the hiker's resultant displacement for the trip, and then find an expression for her displacement. All right, so here we go. I'm going to do the graphical addition first. So on this paper, I scanned it in, and I drew my north, south, east, and west axes, and I took the standard kind of definitions of north being the plus y-axis and east being the plus x-axis. Okay, so my first displacement was 25 kilometers southeast. Okay, so my choice there was I drew something that was 25 kilometers long according to the scales that I had set up. Okay, and I very carefully set my divisions so that they were equal to 5 kilometers each division. Okay, and then I measured out 5 divisions length, and I put that down halfway between my south and my east axis, and I drew my vector A. Okay. Now, the next vector displacement was 40 kilometers at 60 degrees north of east. All right. So what I do for my graphical addition is I start the beginning of my vector B at the end of vector A, right here where I've drawn my new little coordinate system. And then I measured 60 degrees up from my east axis towards north. Okay? And then along that angle, I drew a vector that represented 40 kilometers in length. Then my resultant vector started at the beginning of my first vector and goes to the end of my second vector in a straight line, and that's my resultant displacement. So even without doing any of the math, you can see that my vector is, I don't know, maybe a third of the way north of the east or so, and it's looking like it's going to be somewhere between 25 and 40 kilometers. Okay, so that's kind of an estimate. Now that I've got my drawing up, I can go ahead and talk a little bit about what the angles that are going to be that I'm going to use to do my algebraic method. All right, so one of the vectors, the 40 kilometers at 60 degrees north of east, that's already defined with respect to my plus x-axis, which is east, because I'm swinging north from east. So my angle for my vector B is just going to be 60 degrees, and that's pretty straightforward and easy. But my southeast vector, that's a little weirder, okay? So in order to use the x is equal to r cosine theta kind of definitions, what I have to do is I have to figure out what my angle is swinging counterclockwise from that plus x-axis. Now this vector A is southeast, which is in quadrant 4. So that means that the angle is going to be between 270 and 360 degrees. So my angle theta A starts from this plus x-axis, which is east, and swings all the way around and goes to vector A. And I've shown that in the drawing here at theta sub A. Okay? Now what this is I'm swinging from east to west, and that gives me 180 degrees. And then I'm swinging from west to south, and that gives me 90 degrees. And then, since it's southeast, I know that it's halfway between south and east, and so it's 45 degrees more. So if I add 90 plus 180 plus 45, that gives me angle 315 degrees, okay, for that total angle swinging counterclockwise from the plus x-axis. And that'll be the angle for my vector A. Okay, so now I'm going to use all that information to do the algebraic solution to my problem. So first of all, I have to break my vector A and B up into its vector components. And then the strategy is to add AX plus BX to get my resultant R vector, okay, its X component, and then AY plus BY to get the Y component of my vector. All right, so the X component will be 25 kilometers times the cosine of that theta A, which was 315 degrees, and that's 17.7 kilometers. The y component of vector A will be the length of vector A, which is 25 kilometers, times the sine of the angle, which is 315 degrees, and that gives me negative 17.7 kilometers. Now for my vector B. Vector B has a length of 40 kilometers. To get the x component, I multiply 40 kilometers times the cosine of theta B, which is 60 degrees. And then I get 20 kilometers. And for my y component, it's 40 kilometers times the sine of 60 degrees to get 34.6 kilometers. All right, now for my resultant vector, I need to get the x component, so I add ax plus bx, okay? And that's 20 kilometers plus 17.7 kilometers for 37.7 kilometers, okay? For vector y, I've got ay plus by, okay? So ay is negative 17.7 plus 34.6 to give me 16.9 kilometers. Now, if I want to find the total magnitude of my vector r, the total length, I do the square root of the sum of the squares of the components. So I would do the square root of 37.7 squared plus 16.9 squared. And then when I take the square root of those numbers, I get 41.3 kilometers. And then my angle theta would be the inverse tangent of the y component of the vector over the x. So I've got the inverse tangent of 16.9 over 37.7, and that gives me 24 degrees. And so my vector r is going to be 41.3 kilometers at 24 degrees north of east. So you can see I estimated about a third or so of the 90 degrees. So that would be roughly a 30-degree angle. I got pretty close on the angle, and I said it looked like it was somewhere between 25 and 40, and it's actually a little more than 40. It was about 41.3 kilometers, so I was off by a little bit there. So you see the importance of doing the component method of vector calculation as opposed to the graphical method if you want a really close answer. Okay, so no fears if you're still a little confused. Okay, you can go back over this. You can also read the textbook, and remember that we'll be doing some problems in class that I hope will clear up some of the confusion.